Let's talk about hashing with mutual information. I mean, future neural networks should appear like this because, in hashing, in semantic hashing, we use it for information retrieval, and so here this layer is binary, and it can be proved that it could lead to better generalization. So that's why I really care about hashing with mutual information. Of course, mutual information is just one of ways for semantic hashing, but it is systematic and unifies many of these methods. So this article is really interesting. And so the result, the mean average precision, shows that this mutual information hashing works very efficiently, and we can think of hashing as a supervised learning problem. There are many methods for hashing, as you might know. For example, affinity matching. But affinity matching requires threshold parameter, and so it's controversial because how do you know those thresholds? So it's parameter dependent. Local ranking is the same because it needs margin parameter, and it is controversial again because how do you define this margin parameter? Because sometimes you overfit and underfit, and you don't know how to handle that. But mutual information is parameter free. It means it is free of tuning parameters. And this condition says that we say it has no neighborhood ambiguity, because if for example this x hat has some neighbors, for example this is the positive labels because they are connected to that, but if you go far outside it becomes, so these are negative example because they're too far from x hat. xn, all of these are negative examples. So we want the distance between x hat and xp as small as possible. We don't want errors, and errors means you have ambiguity. So good binary embedding should well separate neighbors and non-neighbors. And we use the Hamming distance. And we achieve low neighborhood ambiguity. There are data-dependent methods. Of course, there are data-independent methods like what? Like locally sensitivity hashing, but it doesn't care about your distribution, the distribution of data. That's why LSH, locally sensitive hashing, is not useful in practice. Although in computer science we use it, but when we go and we want to use it for machine learning, and also even in information retrieval, I don't think it is good, because when you can use data dependent hashing, why do you use locality sensitive hashing? Of course, computer scientists say that, okay, we care about complexity, time complexity, space complexity, and we want to reduce it. And so that's another issue. So there are methods like quantization methods, data-dependent methods, which are like PCA, principal component analysis. There are methods like similarity preserving methods, like, as I said, affinity that needs parameter, local ranking needs parameter. But deep hashing is quite new. Deep hashing methods are supervised, of course, most of them, and they jointly learn the hash mapping and image features with a triplet loss formulation. And as you see, these are very similar because they are cars, so similar to X hat. So we had, as I said, we have X hat. It has some neighbors such as other cars, and dog is very far from cars. So these are negative examples. So it belongs to these negative example. And you see, it has a distribution because some of them has, and we are defining a distance. Distance, of course, it is implicit between x and x hat, but we can represent it by a neural network. I mean, we can define such function, such distance. So, for example, if all of them is 1, for example, phi of x, because it should be binary after all, because it's sign. So it becomes, for example, 1, 1, 1, 1, 1, or divorce, or another extreme case could be 0, 0, 0, 0, 0. And you see, this varies between 0 and b. So it's b, and phi is bidimensional, so it goes to this vector, which is b-dimensional. And as I said, this activation function, we have a sign to make it binary, and of course fi is your activation function. And so we have random variable, the x hat, because for any x hat, and because they apply it for x, it becomes something else. For example, this becomes 3. If you apply it to x prime, it becomes 4. And so the probability that given your membership indicator, for example, given that it belongs to neighborhoods and not non-neighbors, then it can reduce your uncertainty. For example, if I tell you that I know that it belongs to the neighborhood of x hat, then it should reduce. That's why we want to maximize this mutual information, because if this is reduced, this increases the mutual information. They become very dependent. In the linear case, you have correlation. Those are very related to each other. But for a single x hat, it's not enough, because for just you have calculated for one x hat. That's why we integrated over all x hat to have a better measure, and we call it quality measure. But of course, it's intractable, and I tell you how to make it tractable a little bit. So optimizing over a finite training set. So always we change the integral to the sum because we have finite training set. And histogram is the key because you can always represent it by histogram. And of course, these things create discontinuities, and we need gradient for optimization. So how do you deal with lots of these, for example, discontinuity in binarization? All of these things are a problem. So your P depends on phi, and your mutual information here depends on P plus and P minus. And of course, your quality measure here, this is the quality, as I said, this is the integral over all mutual information with different points. So we can always like this, write it like this, but we have a couple of approximation. As I said, this is the continuous relaxation. We relax it using this sigmoid, which is very smooth instead of that sharp, hard binary thing. and the substitution. So after you substitute, we approximate the binary indicator with differentiable one. And of course, during this, we can use this delta function, and so the distance is this. So after a couple of calculations, we have some value which is computed for backpropagation, and we use mini batch again as usual because we have lots of data, and so all of these are just calculations, simple calculations, and this is the mutual information. So we use this mutual information in order to implement semantic hashing. Of course, you can use any other methods, but this is a good method. And this semantic hashing could be used for information retrieval. But I look at it at a different perspective. This you can prove it. I mean, any mathematician could work on a different class of neural networks, but this class of neural networks that you have some layers, and here the bottleneck is just binary. So you're representing your features by some binary in Hamming space, and then because it's discrete, you should choose just one of these sections. So it tries to avoid overfitting. So at least intuitively, you can think about that.